Okay. No. Okay. Amazing. Okay.
I think these guys are static. These are good form. That we don't
You think we're good to start? I just hung off 5. Okay. This is just me testing. Can people on the live stream hear me? So I can just send a message and see the live, say the slideshow. Do you have the slideshow open, David? Were you able to hear it? Can you just see if the audio is working on the slideshow? Hi, everyone. Welcome back to another Battlecode lecture. Last one this week. We'll have another week of lectures next week. Today, we're going to be talking about pathfinding, specifically in Battlecode, but we'll be taking a pretty high-level overview of many different algorithms. And I hope you find it, useful. I suspect this is going to be a fairly short lecture, but again, hope you find it useful. So coming through great, wonderful. So just to get us on the same page, especially if you're newer to this, to programming or to Battlecode in general, when we talking about pathfinding, we're really talking about graphs. So a graph has nodes and it has edges. So in the context of Battlecode, when we talk about a node, we're really talking about a location on a map. So map locations is the actual object. And you want to go from one location to another. So maybe your rat is looking for a rat mine or cheese or another enemy rat to attack. And the whole point of these algorithms is that you want to reach someplace, maybe you're looking for cheese, and you don't know all the information of the map. When you're watching a game in client, you can see everything that's happening, but your robots individually don't know everything that's happening. So that's what we're going to talk about today. I guess I got a bit ahead of myself, but again, nodes, when we talk about nodes, we're talking about map locations, and we're talking about edges. We're talking about how the map locations connect to each other. So if your rat is at some map location, the adjacent nodes, with the way the edges are connected, is just the map locations that are connected to each other. So abstractly, this is a graph, but you should have in your head the map that you see in client with all the locations that all the map objects can be. So we're going to be talking about a couple of different algorithms. Some of them are more useful than others, but we're going to start from the very beginning to give you a sort of conceptual idea of how everything works. We're actually not going to look too deeply at exact like Java or Python code because all of these algorithms are very well studied. They're all available online. So I want to focus instead on a very conceptual high level overview so that you know how these algorithms work and how you can make adjustments for your own programs. So the first algorithms we're going to talk about are very common. You probably have already heard of them, but if you haven't, they're called breadth first search and depth first search. And they're actually almost exactly the same algorithm. It's really just about order. So in a breadth first search algorithm, you're going through, you have a starting node. So in this picture, that's the A, you're at the top. And you're going through and you're saying, what are all the nodes I can immediately access? So in the context of Battlecode, your rat is at a specific location. It's going to look, what are all the map locations I can access? And it's going to go to the next one. So let's go to B. But instead of going further, it's actually going to go back to A in breadth first search. It's going to say, okay, what is a different place I could have gone? We could have gone to C. It's called breadth first search because you're not going deep, you're going out, essentially. You're radiating outwards. Depth first search takes the opposite approach, and it goes in as far as it can. So on the left here, you see that it starts at A, and then it goes to B, and then it goes to, let's say, D, and then to H. It's going as deep as it can before at some point it has to backtrack because it didn't find what it wanted. It didn't find cheese, didn't find a rat mine, didn't find what it wanted. And we can look at broadly the algorithm, but I want to emphasize that we're going to talk deeply about this. This is probably not the algorithm you're going to use, and we're going to talk about why. But I did want to give a conceptual overview. So you have this notion of a queue, which is the places that you want to look for or that you want to look into. And you have a visited set or some sort of object that keeps track of all the places you've already been. And what you're going to do is that while you still have places to explore, so your rat is at a specific rat location, it's going to look everywhere around it, see what places are not occupied by a wall, dirt, another rat. And it's going to say, well, let's add this to our queue. Let's add this to a place that we want to look at. And then you might want to do something. So you might want to check if there's cheese there. You might want to, if there's an enemy rat there, you might want to attack it or not, if you're not going to backstab. Do whatever you want. That's up to you and your strategy. And then when you're at that new location, you're just going to look at all the new places that you can visit. If you haven't visited that, you're going to add it to the queue so that you can explore it later. And you're going to mark your current location as visited, so you don't go back to a place that you've already looked. The only difference between breadth first search and depth first search is how you choose to find the next place to visit. So in breadth first search, you're going to look at your oldest locations. So if a rat is at some location A and it adds to the queue, let's say B and C, and then it goes into B and it adds D, location D, it's not going to go into farther into D. It's instead going to go back to C, which means you're popping from the front. You're looking at the oldest locations you've already visited, and you're going to go from there before you go any deeper. Whereas in depth first search, you're always going to take the newest location that you looked at and explore deeper from there. And yeah. There is a modification of depth first search, which is called the A-star algorithm. I might have said depth first search. I meant breadth first search. And the only fundamental difference is that it adds a sort of heuristic. So when we look at this very simple map here, if the rat is trying to get to the cheese, we as people kind of know that there's probably a good place for the rat to go. The rat is probably going to want to go to the green dot because it's closer to the cheese. And it should not go to that red cross because you're going farther away. But a pure breadth first search or depth first search isn't going to know that unless you somehow tell it how to do so. So in the context of Battlecode, you might say, well, let's compute, when we look at the neighbors that we might choose to go to, let's compute the distance of that new neighbor to the cheese or wherever we want to go. And it's going to say, well, that green location there is closer to the cheese than any other location. And the red location is farther away than any other possible neighbor. So the best possible location you probably want to go to is the green dot. This saves you from having to do a full breadth first search and saves you a bit of time. But this is also probably not going to be an algorithm that you're going to choose because there are some problems with these algorithms. And I wasn't here for yesterday's lecture, but I want to do something different. I want to open up this to all of you and to those of you in the chat. Do you have any ideas as to why breadth first search or depth first search or the A-star algorithm might be a bad choice? Yes.
The biggest one that I've heard is that you much of my own code.
Exactly. So if we go back to this, where's my algorithm? If we go back to this algorithm, it's actually doing it doesn't look like it's doing that much. Where's my mouse? Here we go. It doesn't quite look like it's doing that much because it's fairly short, but it is actually doing quite a lot of work. And that's a lot of it to do with this queue. You're pushing, you're popping from the queue. You're checking like all these, did we already visit this location? It is very bytecode intensive. And in the context of Battlecode, where all of your robots, your baby rats are very limited in how much computational work they can do, probably not a good choice. Any other potential problems? Well, let's talk about a few more. They can also be very memory intensive. So going back to our algorithm here, you have to keep track of a queue, so all the places you want to go, and you have to keep track of a visited set, which can get pretty big if you're doing a lot of movement. Those are all things that, again, you're kind of limited in Battlecode, and especially in like breadth first search in the A-star algorithm, these are kind of not ideal. Another issue, especially with depth first search, is that you really have no idea where you're going to go. Eventually, if the location you want to get to, so if you're looking for cheese, if the cheese is reachable, if it's not blocked completely by dirt or walls or enemy rats, eventually we'll find it. But you might stray off all these different directions before you end up finding your cheese. And there is also one more thing that we've kind of implicitly assumed, is that the graphs aren't changing. So when we go back to here, we're kind of saying, well, we can do all of this because the graph's not changing. This I is not going to disappear. This J is not going to flip around to a different place, or no cheese is going to appear. But obviously, it's pretty unrealistic in the context of Battlecode. People or baby rats are constantly building dirt, digging dirt, adding rats. Cheese mines are adding cheese. So, for example, one specific example is if you have this visited set. Let's say you're looking for cheese. You have a baby rat that's looking for cheese. If it passes through a location that doesn't have cheese, but it's kind of near a cheese mine, and the cheese mine suddenly generates cheese in a place you've already visited, well, the rat's not going to go back to the same location because we said we're not going to look at locations where I visited because there wasn't cheese there before. But now there is. We've kind of made this assumption that the graph aren't changing, even though they are. So these aren't great algorithms in the context of Battlecode, though they are very common. And now we're going to talk about more common algorithms that are used in Battlecode that potentially are less familiar to you. And these are called the Bugnav algorithms. I'm not entirely sure why they're called bug. Actually, kind of wish I did. Go ahead.
I think the reason is because you're like a tiny bug and you
Yeah.
can't see where you're going to walk around.
Right. I was going to say, I think that's exactly it. They're probably, in the earlier days when, again, everything was pretty limited in terms of computation, it's probably, they were looking for very efficient algorithms. Yeah, they're called Bugnav algorithms. And there are multiple versions of it, but they all share some very similar ideas. And the big idea is that because we can't find a perfect path, we're instead just going to pretend that we can move directly towards the location we want to go. So if you imagine that green dot over there is, your baby rat, and the red dot is your cheese. So the green is start and the red is your goal. That's the general terminology. We're just going to draw a straight line, and we're just going to have our rat do our very best to do that. But of course, there might be other baby rats in the way. There might be dirt. There might be walls. So if we encounter such an obstacle, we're just going to try to move around as best as we can. And usually that entails moving in a constant direction or I'm sorry, turning in a direction once we hit an obstacle, and just moving around until we are able to start moving in the direction of our goal again. So looking here, we move towards the wall, we hit the wall. So let's turn again. Oh, now we can move in the direction of the goal again. So let's do that again. Let's move in the direction of the goal. Here's the wall. Move, 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 move. Now we can move in the direction of our cheese. Let's do that. We'll see why. We'll look at some pseudocode, but these are pretty efficient algorithms because they don't require you to store any or not that much information. It's all based on the local information that your robot can immediately see. So you're not saying, well, what are all the places I've already visited? Where are all the walls currently at? We're just saying, move if you can. If you can't, try something else. So this makes it O1 work, if you know what that means. 1 second. And that makes it much more efficient in terms of bytecode. Go ahead.
The sample robot here is going all the way around the wall and not trying to just move towards it when possible, but when it turns the corner, why does it turn again?
Because in general, it attempts, we'll look at some pseudocode, but in general, it just tries to move. It depends on how complex. There are multiple versions of the Bugnav, and I think your question will most be addressed by the best one, Bugnav, Bug 2. But in general, it just tries to move along the wall until it gets closest to the direction that it moved, like in the line that it originally moved. You're not recomputing this line every single time. Once your bot starts moving, it's going to try to always look for this line, even if it's already traveled. So once you're, for example, over here at this corner, it's not going to draw a new line and try to move here, for example. I think that's the question you're trying to get at. It's going to keep going until, oh, here's the line we're at again. Does that kind of answer your question? Well, we're going to look more into it. I think that question will be addressed when we look at the algorithm specifically. So we're going to start with the simplest one, which is called bug 0. And all it really does is exactly what I just said. It's going to start, it's going to look at where we want to go, it's going to look at the end location, it's going to draw that line. And it's going to do this exact process. Go, hits a wall, move around the wall, go, move around the wall, go. There's really not that much to it. It's actually I think it's almost exactly the same length as depth first search and breadth first search, the way we implemented it in the pseudocode earlier. And it's fairly straightforward. But there's a problem with this in that it can kind of get stuck. It can end up in infinite loops, especially with concave surfaces, we'll call it. So if our rat is here and our cheese is at the goal, it will look towards here's the cheese, it will look towards it, move up, hit the wall, so move around, move around. It appears that we can move in direction of the cheese, so let's move there, hit the wall, move around, move around, move around, move around, and we're back at where we started. And it has no idea that it did that, because again, we're not storing that much information. So it's just going to do the whole loop again, and this will cause an infinite loop. Clearly, this is a problem. So we're going to update our version. Let's go to bug 1. Here in bug 1, we are going to store some information. And particularly, we're going to store, as we move along the object, we're going to store the location in which we minimize the distance to our goal. So if we imagine we're still at bug 0, we're going to, here's our sort of straight line. We're going to move, hit the wall. We're going to go around, we're going to go around, we're going to go around. But this entire time, we're keeping track of the distance that minimizes, or we're keeping track of the point that minimizes our distance to the goal. So as we're moving around, we're doing this computation, and we find this blue line minimizes this distance. But we don't know that it's minimizing until we've actually moved all the way around. So we're going to keep going around the object. We're going to keep going, we're going to keep going. Oh, we're back at where we started. Now that we're back at where we started, now we're going to say, okay, what was that point? What was that minimizing point? Let's loop back around, let's backtrack. Let's go back to that point. Now that we're back, let's try moving directly to the line, to the goal again. And at this point, we're going to draw a new line. So at this point, yes, we do draw a new line. And we're going to essentially apply the bug 0 algorithm again. Let's move directly towards the goal, to the cheese. Oh, we hit a wall. Let's keep tracking. Let's keep going around the object. Keep going, keep going, keep going. Now we're back at where we started. And this entire time, we've been keeping track of the point that had minimum distance to our goal, which was this blue point. So let's backtrack all the way over until we hit that point. And let's try moving directly to the cheese. And it's actually quite close, and there it is. I hope you see that this is probably not super efficient because you are doing a lot of looping and backtracking. It'd be nice if you had some notion of, like, hey, we're pretty close. Let's just stop while we're ahead and go forward. And I will say a nice thing about bug 1 is that similar to breadth first search and depth first search, actually, it is guaranteed to find you the location. It's guaranteed to find you a path eventually. If you give it enough runtime, if you let it do its thing, it will find a path eventually. Unlike bug 0, which can go around an infinite loop. But again, pretty inefficient. So let's see if we can update our version again. So let's look at bug 2. This is the algorithm that probably most of you will implement. I believe this is a pretty popular one among the finalists and the top competitors. And we actually bring back this line again. And we're going to draw it very explicitly. And like in bug 0, we're going to move directly towards our goal. And we hit the walls, let's move around and move around it. And we keep going until we re-intersect that line, or intersect that line again. So what that tells us is, hey, we've somehow gotten closer to the goal. And that tells us, let's stop moving around this object. We're not going to keep going. We're not going to keep going and looping around. Let's just stop here. We've gotten closer. And let's just try again. So let's move closer to our object, to our goal, to the cheese. Move. We hit the wall. And let's keep going. Move around the wall. Oh, we intersected the line again. So let's try moving towards the cheese. And we hit the goal. Like bug 1 and depth first search and breadth first search, this is guaranteed to reach any reachable goal. So as long as your cheese or your cheese mine or your enemy route, whatever, as long as it's reachable, it's not completely surrounded by dirt or walls or whatever, you'll eventually find the path. And this is a very efficient one, especially in comparison to bug 1, which does all this looping around. And it's also very memory efficient because the only thing you really have to store is this line, and you don't recompute it every time as you're moving. And you also don't need to keep track of your best points like in bug 1. So this is a very, very efficient algorithm. And while it does not guarantee the optimal path, given the constraints of the bytecode restraints and the memory restraints in Battlecode, this is an excellent algorithm for you to implement. I realize I should have stopped earlier, but does anyone have any questions about anything, any of the algorithms? Because we're actually almost done. This is a very short lecture today. Yes. So there is another algorithm, which I actually regret not putting on here. But essentially, you have to figure out for yourself that this is, again, it's freely available online. Like this is very well studied. You will find this. And if you want more details, you can come to office hours here. But there's an algorithm that essentially computes this line for you. And I believe it's stored as just like some sort of list in Python or an array list in Java that is all the map locations that make up this line. And so you just say, oh, if I as I'm moving around, I check my location against this list. And if it's in this line list, we've hit the line. That's the big idea. And again, just sort of a pseudocode overview. If we can move towards the wall or move towards the goal, let's just do that. If we hit an obstacle, well, let's just try moving around it until we re-intersect. I'm sorry. For some reason I'm blanking, but until we intersect the line again. So I believe that happens here. So we're following the wall and we intersect the line. And if we end up closer to our goal, well, we should stop there and move towards our cheese. So we're not going to keep following the wall. Instead, we're going to come over here and we're just going to move directly towards the goal. And that's the whole point of this distance function. We're keeping track. We're making sure we're not going farther away. Because you can imagine a weird sort of scenario in which if we imagine this line coming back over here, and maybe we have more walls over here. If our robot is coming over here, we don't want to, when we intersect the line back here, we don't want to say, well, this is good, because it's not. We actually gotten farther away. We should continue until we wrap back around and get to a place that's closer. And yeah, does anyone have any final questions about algorithms that we have talked about? All right. And I do want to bring up one point in that this year's Battlecode is kind of different from previous years. I'm not going to say that it's completely unique because I'm not sure of all the Battlecode competitions we've had in the entire history of the program. But this year's kind of different in that we have vision cones, in the sense that your baby rats cannot see all the locations around it. They can only see a certain field of view in front of it. We wanted to emphasize that this does not fundamentally affect any of the algorithms we've talked about. All it really does is it reduces the information you have. And how you deal with this is essentially a strategy choice that you're going to make. Are you potentially going to have your rats turning a lot? Are you going to maybe pair up rats so that they can, communicate with each other? That is up to you, but I wanted to emphasize that the vision code does not essentially affect these algorithms. You can implement these more or less without problem. So if you've done Battlecode in the past and you've worked with these algorithms before, nothing changes too much. And that is actually all I had for today, unless anyone has any questions or if you wanted to come to office hours and ask more details about these algorithms. No. Then we are done for today. And I guess we are moving right into office hours. Thank you, everyone.
Yeah, you're good. You can go through all this.